Picture this, the last flicker of light fading into endless darkness, the final whisper of heat dissolving into cold, empty silence, the universe as we know it gone. Not with a bang, but with a whimper or perhaps a violent, unimaginable tear. This isn't just science fiction. It's the inevitable fate awaiting our cosmos, a destiny written in the laws of physics themselves. And while it might sound like the plot of a dystopian epic, these apocalyptic scenarios are very real possibilities, each one more mind-bending than the last. From the slow, icy grip of heat death to the cataclysmic crunch of a collapsing universe, the ways our cosmos could meet its end are as varied as they are terrifying and fascinating. What if I told you there isn't just one way the universe could die, but 25? Some theories paint a quiet, almost poetic ending where stars flicker out one by one, leaving behind a vast, dark graveyard. Others describe a far more dramatic finale, a cosmic shredding so violent it would rip apart galaxies, planets, even atoms themselves. And then there's the haunting idea that our universe might be destined to collapse back into itself, reversing the Big Bang in a fiery crescendo. These aren't just wild guesses, they're rigorously studied scientific theories, each backed by equations, observations, and the relentless curiosity of humanity's greatest minds. So why should we care about events so far in the future that they might as well be myth? Because the fate of the universe isn't just a story about distant galaxies and abstract physics, it's a mirror reflecting our deepest questions about existence, time, and our place in the grand scheme of things. Whether it's the chilling silence of heat death or the explosive drama of the Big Rip, each scenario forces us to confront the fragility of everything we know. And as we explore these 25 cosmic doomsdays together, you'll discover something unexpected. Even in the face of ultimate endings, there's a strange, breathtaking beauty to the universe's grand design. So buckle up, this journey isn't just about how the cosmos dies, it's about understanding the incredible story it's telling right now, with every star, every galaxy, and every fleeting moment of light. If the universe has a quietest, most patient way to end, it's heat death, a slow fade into oblivion where even time itself becomes meaningless. Think of it like a cup of coffee left out on the counter. No matter how hot it starts, eventually it cools to match the temperature of the room around it. Now imagine that same principle applied to the entire cosmos. Over trillions upon trillions of years, stars will exhaust their fuel. Galaxies will drift apart, and every last bit of heat, every flicker of energy will spread out until the universe is nothing but a vast, uniform graveyard. No more blazing suns, no swirling nebulae, just an endless, lukewarm void where nothing ever changes. This isn't science fiction. It's the unavoidable result of one of physics' most unbreakable laws, entropy. In simple terms, entropy is the universe's way of spreading things out, energy, heat, even particles, until everything is perfectly balanced with no usable energy left. Every time you light a match, cook a meal, or even take a breath, you're contributing to that slow march toward equilibrium. And in the far, far future, after every star has burned out and every black hole has evaporated, entropy will win. The cosmos will reach maximum disorder, a state where nothing can happen because there's no energy left to make anything happen. What does that look like? Picture a space so cold that atoms barely move. No new stars ignite, no planets orbit. Even black holes, the last holdouts against this crushing stillness, will eventually vanish, radiating away their energy until they too dissolve into darkness. Time, which once marched forward with purpose, loses all meaning when nothing changes anymore. There's no past or future, just an endless, unchanging present. It's a fate so quiet, so total, that not even the ghosts of galaxies remain. Yet there's something strangely poetic about it. Heat death isn't violent or sudden. It's the universe exhaling its last breath, settling into eternal rest. And in that eerie, frozen equilibrium, we find one of the most profound truths of physics. Everything, no matter how vast or enduring, must one day fade. But what if the universe doesn't fade quietly into the cold? What if its fate isn't stillness but fire? Enter the Big Crunch, a cosmic doomsday where the expansion we take for granted suddenly reverses, and the entire universe comes crashing back together in a spectacular, catastrophic collapse. Imagine the Big Bang played in reverse. Galaxies that once raced apart now hurtle toward each other. Stars collide in dazzling explosions, and space-time itself crumples like paper in a closing fist. This isn't just an ending, it's a cosmic reset button where everything that ever existed gets compressed back into a single, infinitely dense point. At the heart of this theory lies gravity, the universe's most patient architect. For billions of years, dark energy has been pushing galaxies apart, stretching the fabric of space itself. But in the Big Crunch scenario, gravity finally wins the tug of war. Maybe dark energy weakens over time, or perhaps there's just enough matter in the cosmos to outweigh its push. Whatever the reason, once expansion slows to a stop, gravity takes over with terrifying efficiency. Clusters of galaxies begin merging, their combined mass pulling others inward faster and faster. Space contracts, temperatures soar, and the universe becomes a pressure cooker with no escape. The final moments would be apocalyptic beyond comprehension. As everything condenses, the cosmic microwave background, the fading glow of the Big Bang would heat from nearly absolute zero to thousands of degrees, then millions, then more. Stars wouldn't just die, they'd be vaporized in the rising inferno. Planets, asteroids, even the atoms composing them would break apart under pressures greater than neutron stars. And as the last black holes merge, their singularities combine into one all-consuming maw, swallowing the entire universe back into the singularity from which it sprang. Here's where things get stranger. Some theories suggest this might not be the end at all, but a rebirth, a big bounce, where the collapsing universe rebounds into a new Big Bang, birthing an entirely new cosmos. It's a cyclical vision of existence where universes rise, expand, collapse, and repeat like cosmic seasons. There's even speculation that fundamental constants, the very laws of physics, might reset in each cycle, meaning the next universe could be utterly unrecognizable from our own. Yet whether it's a one-time implosion or part of an endless cycle, the Big Crunch forces us to confront an unsettling truth. Everything we know, every galaxy, every planet, every fragile moment of life, exists in a fleeting balance between expansion and collapse. It's a reminder that even the mightiest forces in existence are temporary, caught in a dance between creation and destruction that we're only beginning to understand. Now imagine a force so relentless, so utterly unstoppable, that it doesn't just erase the universe, it shreds it, atom by atom. This is the Big Rip, where dark energy doesn't just push galaxies apart, it weaponizes the expansion of space itself, accelerating until the fabric of reality is torn apart at the seams. Unlike the slow fade of heat death or the fiery collapse of the Big Crunch, the Big Rip isn't patient, it's violent, cataclysmic, and it could happen far sooner than we ever imagined. At the heart of this nightmare scenario lies a special kind of dark energy called phantom energy, a hypothetical form so potent that its strength grows over time. Normal dark energy, the stuff we think is driving cosmic expansion today, keeps a steady push, but phantom energy, it's the universe hitting the gas pedal harder and harder until expansion spirals out of control. Picture a rubber band stretched tighter and tighter until it snaps. Only in this case the rubber band is space-time itself. Here's how the end would unfold. Tens of billions of years from now, though some models suggest it could be much sooner, the acceleration would reach a breaking point. First, galaxy clusters would be ripped apart, their gravitational bonds no match for the raging expansion. Next, individual galaxies would unravel, stars flung into the void like sparks from a bonfire. Then, as phantom energies grip titans, solar systems would disintegrate, planets torn from their orbits in an instant. But the horror doesn't stop there. In the final moments, even atoms would be no match for the onslaught. The forces holding nuclei together would fail, particles ripped apart as space itself expands faster than the speed of light at a local level. Time and space, the very framework of existence, would dissolve into chaos. The universe wouldn't just die, it would be annihilated from the bottom up, leaving behind nothing. No remnants, no echoes, not even the possibility of something new. Recent research has made this scenario even more unsettling. Some models suggest phantom energy could trigger the Big Rip in as little as 22 billion years, a blink in cosmic terms. Others propose that if dark energy's equation of state, a key factor in its behavior, dips below a critical threshold, the countdown could start even sooner. It's a chilling reminder that the universe's demise might not be a distant abstract, it could be a ticking clock with a deadline far closer than we think. Yet in this terrifying possibility lies a profound irony. The same force that birthed the universe expansion could be the very thing that destroys it. It's a cosmic twist of fate where the engine of creation becomes the instrument of annihilation. And as scientists race to understand dark energy's true nature, one question looms larger than all others. Is the Big Rip our destiny, or just one of many possible endings waiting in the dark? There's a quiet fear lurking in the equations of quantum physics, a doomsday so sudden, so absolute that the universe wouldn't even have time to scream. It's called vacuum decay, and it hinges on a terrifying possibility. What if the fabric of reality itself is built on unstable ground? Right now, we exist in what scientists call a false vacuum, a seemingly stable state that could at any moment collapse into something far more fundamental and far more deadly. Picture the Higgs field, the invisible energy field that gives particles their mass like a marble resting at the top of a hill. It seems stable, but give it the slightest nudge, and it could tumble into a lower energy state, a true vacuum. If that happens anywhere in the universe, a bubble of this new reality would form, expanding outward at the speed of light. Inside that bubble, the laws of physics as we know them would rewrite themselves. Atoms gone, forces like gravity and electromagnetism erased. Every structure in existence, from stars to cells, would dissolve into chaos before anyone could even blink. The scariest part, it could already be happening. A single quantum fluctuation in some distant corner of space might have already triggered the bubble. Because it expands at light speed, we'd have zero warning. One moment, everything's normal. The next, an invisible wall of annihilation sweeps through Earth, rewriting existence itself. And there's nothing we could do, no outrunning it, no fighting it. The universe wouldn't just end, it would be replaced with rules so alien that even the concept of ending might not apply anymore. Some theories suggest the Higgs field is just stable enough to avoid this fate for now, but others argue that high-energy experiments or cosmic events could tip the balance. It's a cosmic game of Jenga where one wrong move could bring everything crashing down. And while the odds might be slim, the stakes couldn't be higher. Because if vacuum decay is real, the universe's final moments wouldn't be a slow fade or a fiery collapse, they'd be a silent, instant erasure, as if we never existed at all. In the vast, cold reaches of deep time, black holes may become the last rulers of a dying universe. After galaxies fade and stars burn out, these gravitational monsters will linger silent, insatiable, and utterly inescapable. Picture a cosmos where entire constellations have vanished, where the only light comes not from stars, but from the faint, dying glow of matter spiraling into oblivion. This is the black hole era, a phase lasting trillions upon trillions of years, where the universe's final structures aren't galaxies or nebulae, but singularities pulling the last remnants of existence into their grasp. At first, black holes feast, Drifting through the void, they swallow rogue planets, wandering stars, even other black holes, growing more massive with every collision. For a time, they'll be the only source of energy in the cosmos, their accretion disks shimmering like ghostly halos in the darkness. But even these cosmic titans aren't immortal. Thanks to Hawking radiation, a quantum quirk predicted by Stephen Hawking, black holes slowly leak energy, particle by particle, over timescales so vast they dwarf the current age of the universe. The larger the black hole, the slower it evaporates. Supermassive ones could take a googol years, that's a 1 followed by 100 zeros, to vanish. As the eons crawl forward, the universe becomes a graveyard of evaporating relics. Smaller black holes disappear first, their final moments marked by a burst of radiation as they unleash their pent-up energy in a silent, invisible flash. Space grows colder, darker, emptier. Eventually, even the mightiest black holes succumb, their once unthinkable masses reduced to a whisper of particles and faint photons drifting through an endless void. But here's where the story twists. Some theories suggest that in these final moments, as the last black hole evaporates, something bizarre might happen. The release of Hawking radiation could, in the most speculative models, trigger a spontaneous rebirth, a quantum fluctuation so rare it reignites existence itself. It's a cosmic Hail Mary, a chance for the universe to start anew from absolute nothingness. Whether that's a comforting thought or a haunting one depends on how you view eternity, but one thing's certain. In the black hole era, the universe's final chapter is written not in fire or ice, but in the patient, inevitable unraveling of gravity's last grasp. Somewhere in the unimaginably distant future, long after black holes fade and even the vacuum of space grows cold, there might come a moment when the very fabric of matter itself unravels. Not from an outside force, not from a cataclysmic event, but from within. This is the eerie fate known as proton decay, where the particles that make up everything from stars to human bodies could simply dissolve. We've always assumed protons are stable. After all, they're the backbone of atoms, the unshakable foundation holding reality together. But grand unified theories, the ambitious frameworks attempting to merge all fundamental forces, suggest something unsettling. Protons might not last forever. If these theories are correct, the building blocks of existence have an expiration date, ticking down over time scales so vast they make the age of the universe seem like a fleeting instant. Here's how it would unfold. Over quadrillions of years, protons, normally indestructible, could spontaneously break apart due to quantum quirks we don't yet fully understand. They wouldn't just vanish. Instead, they'd decay into lighter particles, positrons, neutrinos, flashes of energy with no structure or purpose. Imagine a sandcastle slowly collapsing grain by grain, except the sand itself is disappearing. First, hydrogen atoms, the simplest and most abundant, would fade, their lone protons decaying into nothingness. Then heavier elements would follow, their nuclei crumbling as protons wink out one by one. Without protons, atoms can't exist. Without atoms, molecules disintegrate. And without molecules, every star, every planet, even the dust floating between galaxies would dissolve into a thin, useless mist of subatomic debris. The universe wouldn't just be empty, it would be irreversibly empty, with no material left to ever form new structures again. There's a haunting beauty to this idea. It's not a violent end, not a dramatic collapse. It's a slow, quiet undoing of existence itself, where matter, the very stuff of reality, simply ceases to be. And yet, in that silence, there's an odd comfort. If protons do decay, it means the universe isn't just running out of energy, it's transforming, recycling itself on levels so profound we can barely comprehend them. Maybe, just maybe, those scattered particles become the raw ingredients for something entirely new, a cosmic cycle playing out on scales beyond human imagination. For now, proton decay remains hypothetical. Experiments deep underground, shielded from cosmic rays, have searched for traces of decaying protons and found nothing. But absence of evidence isn't evidence of absence. If protons do decay, it could take 10 to the power of 34 years or longer, numbers so vast they defy meaning. Yet the possibility lingers, a whisper in the equations of physics reminding us that even the most permanent-seeming things might only be temporary. And if that's true, then everything, from the mountains outside your window to the stars above, is already invisibly counting down. The Big Bang wasn't just an explosion, it was a stretching, a cosmic inflation so rapid it made light seem slow. For a fraction of a second, the universe expanded faster than the speed of light itself, smoothing spacetime into the vast, flat expanse we see today. But what if that inflation never stopped? What if, somewhere in the cosmos, a patch of spacetime is still inflating uncontrollably, ballooning into a runaway bubble of reality that could tear our universe apart from the inside? This isn't just a thought experiment. It's a genuine fear lurking in the math of cosmology, a scenario called hyperinflation, where the very mechanism that birthed our universe could become its executioner. The danger lies in the Higgs field again, the same quantum field that gives particles mass. During cosmic inflation, this field was trapped in a high-energy state, like a ball balanced on a hill. When it finally rolled down, that energy was released as matter and radiation, igniting the hot soup of the early universe. But some theories suggest pockets of space might have gotten stuck or could even re-enter that high-energy state. If that happens, a new inflationary bubble could form, expanding at light speed, its edge not just pushing matter aside but rewriting the laws of physics as it goes. Inside that bubble, space would stretch so violently that atoms, stars, even space-time itself would be torn to quantum confetti. Here's where it gets stranger. This isn't just about destruction, it's about creation. Many physicists believe our universe is just one bubble in a foaming multiverse, where infinite inflationary bubbles nucleate endlessly, each birthing its own cosmos with different physical constants. In that view, hyperinflation isn't an end, it's a cosmic replacement, our universe overwritten by a new one with rules we can't predict. Somewhere out there, right now, a bubble of hyperinflating space might be growing, unstoppable as it chews through dimensions. We'd never see it coming. The bubble's edge would move at light speed, giving no warning before it hits. One moment you're sipping coffee on Earth, the next the coffee, the cup, the atoms in your hand cease to exist as you know them, their properties scrambled by a new set of fundamental forces. The cosmic microwave background, the last echo of our Big Bang, would vanish mid-measurement. Even black holes, those indestructible titans, would be erased not by gravity but by space-time itself unraveling. Yet there's a twisted silver lining. If hyperinflation spawns new universes, then our own demise might just be someone else's genesis. We could be living in the aftermath of another universe's hyperinflation. Our entire existence, the aftermath of a cosmic reset we'll never comprehend. It's a humbling thought. The same force that crafted our reality could one day recycle it, leaving behind not ruins but beginnings we'll never see. Cosmic strings, theoretical filaments of pure spacetime defect, might be the jagged cracks that finally shatter reality. Picture them as scars from the universe's birth, infinitesimally thin but unimaginably dense, left over from the violent symmetry breaking moments after the Big Bang. Most of the time, they drift harmlessly through the cosmos, invisible and inert. But if even one interacts with a false vacuum bubble, that's when the big slurp begins, a doomsday where vacuum decay doesn't just spread, it accelerates, racing along these cosmic fault lines like fire along a fuse. The process would be deceptively simple. A cosmic string passing through an unstable patch of spacetime could act as a trigger, lowering the energy barrier needed for vacuum decay to start. Once initiated, the new, lower-energy vacuum wouldn't just expand outward in a sphere, it would surge along the string's length at near light speed, branching out like lightning through the universe's scaffolding. Entire galaxy clusters could be rewritten instantaneously, their physical laws abruptly swapped for something unrecognizable. What makes this scenario uniquely terrifying isn't just the speed, but the inevitability. Unlike random quantum fluctuations, cosmic strings are persistent structures. If one exists in our cosmic neighborhood, it's only a matter of time before it brushes against the wrong quantum field. And when it does, the resulting phase transition wouldn't just change the universe, it would dissect it, carving reality into disconnected islands of doomed spacetime. Some models suggest these strings could even create domain walls, two-dimensional sheets where the old and new vacuums collide. Crossing such a boundary might mean instant annihilation, not from heat or force, but from suddenly existing in a region where your very atoms no longer obey the rules keeping them stable. The universe wouldn't end with a uniform fade to black, but as a patchwork quilt of incompatible physics, each fragment sealed off from the others by unbreachable barriers of rewritten law. Yet there's a bizarre counterpoint to this horror. If cosmic strings are real and some gravitational wave observatories are searching for their faint tremors, they might also be threads woven into the universe's grand design. Their catastrophic potential could be balanced by their role in shaping cosmic structure, perhaps even seeding galaxy formation. It's a cosmic irony that the same defects capable of erasing reality might also have been essential to creating it. The Big Slurp isn't just an ending, it's a reminder that existence hangs by threads we're only beginning to see. Hidden somewhere beyond the edge of our observable universe, another cosmos might be dying in a way that dooms us all. This is the nightmare of false vacuum bubbles, not just the decay of our universe, but the terrifying possibility that a neighboring reality has already collapsed, sending a lethal wave of rewritten physics racing toward us at the speed of light. Picture a soap bubble floating through the air, but instead of soap, its surface is pure annihilation. Where it touches, matter unravels, forces reconfigure, and existence as we know it ceases without warning. The math behind this is chillingly plausible. If another universe underwent vacuum decay, perhaps with a Higgs field more unstable than ours, it would spawn a sphere of destruction expanding eternally. Given the infinite expanse of the multiverse, if it exists, such bubbles could be countless, drifting through higher dimensional space like shrapnel from cosmic detonations we'll never see coming. And if one intersects our universe, the moment of collision wouldn't be an explosion or an impact, it would be a silent, instantaneous overwrite. The very constants holding atoms together, the strength of gravity, the charge of an electron, could flip to new values, rendering stars, planets, and life itself impossible under the new rules. What makes this scenario uniquely horrifying isn't just the destruction, but the inevitability. Because the bubble moves at light speed, there's no signal, no advance warning that could ever reach us. Astronomers might observe distant galaxies winking out one by one as the frontier approaches, but by the time we see it, the bubble's edge would already be upon us. The final moments would be eerily quiet, no sound, no tremors, just the sudden realization that the laws of physics have shifted beneath your feet. 1 nanosecond, you're here. The next, your neurons can no longer fire because electromagnetism itself has been redefined. Yet there's a bizarre twist to this apocalypse. Some theorists suggest these bubbles wouldn't just erase, they might transform. If the new vacuum state permits complexity, our universe could be rebooted with entirely different physics, birthing strange new structures beyond our imagination. It's a cosmic Russian roulette where the bullet might kill the universe, or reload it with an entirely unknown set of rules. And if the multiverse is infinite, this might have already happened countless times, with bubbles of alien physics colliding, merging, and overwriting each other in an endless, invisible war of existence. The irony is exquisite. The same cosmological inflation that birthed our universe could have seeded countless others, each a potential time bomb of instability. We float in a cosmic minefield where the gravest threat isn't within our universe at all, but lurking beyond the boundaries of everything we can see. And if that bubble is out there, hurtling toward us right now, there's nothing to do but marvel at the fragility of reality and hope the dice of eternity roll in our favor just a little while longer. What if the universe doesn't truly end but instead gets a second chance? The Big Bounce reimagines the fiery collapse of the Big Crunch not as a finale, but as a cosmic rebirth. Picture the universe contracting into a single, infinitely dense point, only to rebound with a new Big Bang, birthing an entirely fresh cosmos from the ashes of the old. This isn't just poetic symmetry, it's a serious hypothesis rooted in quantum gravity, where the laws of physics twist and warp under conditions so extreme they defy imagination. At the heart of this theory lies a daring idea that gravity, when compressed to its limit, might flip from an attractive force to a repulsive one. Think of it like a spring. Push it down hard enough and it snaps back with equal force. In the Big Bounce scenario, the universe's collapse wouldn't end in a singularity's infinite density. Instead, quantum effects would kick in, creating a cosmic bounce that sends space-time exploding outward again. It's a universe with no true beginning or end, just an endless cycle of expansion, contraction, and renewal. But here's the twist: not all bounces might be created equal. Some quantum gravity models suggest each cycle could subtly alter the fundamental constants of nature. The speed of light, the strength of gravity, even the charge of an electron. These might reset with each iteration, meaning every new universe could operate under completely different rules. One cycle might spawn a cosmos where stars burn forever. Another could produce a lifeless void where matter never clumps together. The question isn't just whether the universe bounces, but whether it remembers anything from its past lives. Critics argue there's a fatal flaw: entropy. Each bounce would carry forward the universe's increasing disorder, making subsequent cycles shorter and more chaotic. If true, the Big Bounce isn't eternal, just a slowing pendulum winding down toward a final, irreversible collapse. Yet other theorists propose wildcards like quantum fluctuations injecting fresh energy into each rebirth, or hidden dimensions redistributing entropy in ways we can't yet model. The beauty of the Big Bounce isn't just in its grandeur, it's in the questions it forces us to confront. Are we living in the first universe or the trillionth? Could fragments of past cycles linger like echoes in the cosmic microwave background? And if the bounce is real, does that mean every ending is secretly a beginning, waiting for its chance to unfold? The Big Freeze isn't just another name for heat death, it's the universe winding down like an old clock, its gears slowing until they finally stop. Imagine a cosmos where the last stars have flickered out, their ashes cooled into black dwarfs, dark, inert spheres of carbon and oxygen floating in the void like cosmic tombstones. Galaxies, once vibrant with light and motion, now drift apart in silence, their gravitational bonds stretched thin by relentless expansion. This is the Big Freeze, a slow, chilling finale where the universe doesn't just run out of energy, it runs out of the ability to create anything new. What makes this scenario distinct from heat death is its focus on structure. Heat death describes a universe where everything reaches the same lukewarm temperature, but the Big Freeze is about the exhaustion of star formation itself. Over trillions of years, the raw materials for new stars, hydrogen and helium, will either be locked inside dead stars or dispersed so widely they can never reunite. Star-making factories like nebulae will vanish, their gas clouds too diffuse to collapse under gravity. Even the rare collisions between brown dwarfs or white dwarfs, which might briefly reignite nuclear fusion, will become impossible as distances between objects grow too vast. The last visible objects in this frozen era, black dwarfs, the hypothetical end stage of white dwarfs that have radiated away all their heat. Unlike the dramatic explosions of supernova or the eerie glow of neutron stars, black dwarfs are cold, dark, and utterly inert. They're the universe's final fossils, made of crystallized carbon, essentially diamond planets the size of stars. And because protons might not yet have decayed depending on which model you follow, these relics could persist for incomprehensible spans of time, orbiting nothing in the abyss. Yet the Big Freeze isn't just about what remains, it's about what's lost. The universe's expansion will sever the last threads of connectivity. Today, we see galaxies bound in clusters, but in the distant future, even those clusters will dissolve. The sky, once filled with the glow of 100 billion suns, will go dark. Any civilization still clinging to existence would witness their cosmic neighborhood emptying out, like watching neighbors' houses vanish one by one into an impenetrable fog. Telescopes would reveal nothing but endless blackness, the cosmic microwave background redshifted into oblivion. There's a quiet tragedy in this ending. The Big Freeze isn't sudden or violent, it's the universe forgetting itself piece by piece. No grand collapse, no apocalyptic rip, just a fading into irrelevance. And yet, in that fading, there's a strange grandeur. The universe doesn't die screaming, it settles into silence, its story written in the slow, inevitable dispersal of everything that once was. Imagine a cosmic game of dominoes where each falling piece unleashes a blast of energy so intense it could wipe out entire galaxies. This is the terrifying potential of neutron star mergers, one of the most violent events in the universe, capable of triggering an apocalyptic chain reaction. When two neutron stars collide, they don't just create gravitational ripples, they unleash gamma-ray bursts, beams of radiation so powerful they outshine all the stars in their host galaxy combined. Now picture this happening not just once, but in a cascading series across the cosmos, turning the universe into a firing squad of lethal energy beams. Neutron stars are already extreme by nature, city-sized remnants of dead stars, packing more mass than the sun into a sphere no wider than Manhattan. Their collisions are rare, but in the far future, as galaxies grow denser with stellar remnants, the odds shift. Black holes might dominate eventually, but there's a window, a dangerous era, spanning trillions of years when neutron stars could drift close enough to collide frequently. Each merger would send a gamma-ray burst slicing through space, sterilizing any planets caught in its path. And here's where things get worse. These bursts could trigger more mergers. How the energy from one blast might nudge nearby neutron stars out of equilibrium, destabilizing their orbits and sending them spiraling toward one another. Like a row of falling dominoes, each collision could set off another, creating a runaway reaction. Galaxies would become minefields, their neutron stars exploding in sequence, flooding the cosmos with radiation capable of ionizing entire galactic clusters. Life, no matter how resilient, wouldn't stand a chance. This speculative doomsday hinges on an unsettling truth. The universe isn't static. As stars die and galaxies evolve, new threats emerge. We're lucky to exist in a relatively quiet era where such collisions are rare, but the far future might not be so forgiving. Some models suggest that during the degenerate era, when normal stars are extinct and only stellar remnants remain, neutron star mergers could peak, turning the cosmos into a shooting gallery. Yet there's a haunting beauty to this scenario. These explosions, for all their destructive power, are also cosmic alchemy labs. They forge gold, platinum, and other heavy elements, scattering them into space to seed future generations of stars and planets. In a twisted way, the universe's deadliest fireworks might also be its most creative, a reminder that even in annihilation, there's the spark of something new. Dark energy might seem constant now, but what if it's secretly evolving, growing stronger, weirder, or even predatory? This isn't science fiction. Some of the most compelling models in cosmology suggest dark energy isn't just a steady force pushing galaxies apart. It could be a shapeshifter, one that mutates over time with consequences far worse than the Big Rip. Enter quintessence, a theoretical form of dark energy that doesn't just accelerate expansion. but changes its behavior based on conditions we don't yet understand. Think of dark energy today like a car cruising at a steady speed. Quintessence, though, it's a car with a mind of its own, one that might suddenly slam the gas pedal or veer off the road entirely. In some versions of this model, dark energy's strength is tied to an invisible quantum field that can shift states, like water freezing into ice. If that field transitions to a lower energy level, dark energy could vanish overnight, causing the universe to collapse under gravity's weight. Alternatively, it might surge in power, tearing apart not just galaxies but space-time itself at a subatomic level. The stakes couldn't be higher. A single quantum fluctuation in this field could rewrite the fate of everything. The equation of state, a key number describing dark energy's pressure and density, holds the clues. Right now, it's eerily close to -1, the magic value for steady acceleration. But if that number dips even slightly lower, things spiral out of control. Picture a snowball rolling downhill, gathering mass and speed until it's an avalanche. In this scenario, dark energy's push becomes exponential, accelerating so violently that it overpowers every other force in nature. Atomic bonds, the fabric of space-time, even the event horizons of black holes would be obliterated in what physicists call the Little Rip, a slower but equally gruesome cousin to the Big Rip, where structures are stretched apart molecule by molecule over billions of years. Yet quintessence isn't the only nightmare hiding in the math. Phantom energy, a particularly vicious form of dark energy, could grow stronger over time, its density increasing as space expands. It's like a fire that burns brighter the more you starve it of oxygen. If phantom energy exists, it might already be on an unstoppable path to rip the universe apart, with the equation of state plummeting below -1. Recent observations of supernova and galaxy clusters hint that dark energy might not be perfectly constant, leaving the door open for these doomsday scenarios. The most unsettling part, we'd have no warning. Dark energy's evolution would play out on cosmological timescales, invisible in our brief human snapshot of the universe. By the time telescopes detected a shift, it could already be too late. The cosmos doesn't care about giving notice, it operates on its own indifferent clock. And if dark energy decides to change the rules, reality itself could unravel before we even grasp what's happening. But here's the twist. This terrifying uncertainty is also what makes dark energy so fascinating. Its potential to evolve means the universe's fate isn't set in stone. Maybe dark energy will fade, allowing gravity to pull everything back together in a big crunch. Or perhaps it will transform into something entirely new, a force we can't yet imagine. One thing's certain. The mystery of dark energy isn't just about how the universe ends, but how alive and unpredictable it truly is. Somewhere in the depths of space, lurking since the first fraction of a second after the Big Bang, there might be cosmic strings, filaments of pure space-time defect thinner than a proton but with the mass of a mountain range. These aren't mere hypothetical oddities, they're scars left over from the universe's violent birth, when the very fabric of reality underwent a phased transition like water freezing into ice. And if even one of these strings were to suddenly snap, the energy released could be cataclysmic enough to rewrite the rules of existence in an instant. Imagine plucking a guitar string so tightly wound that its vibration could level a city. Now scale that up to cosmic proportions. A string light years long, vibrating with enough pent-up energy to warp spacetime itself. When cosmic strings snap or intersect, they don't just dissipate quietly. Theoretical models suggest they could unleash bursts of gravitational waves powerful enough to distort entire star systems, or even carve temporary knots in spacetime where the laws of physics break down entirely. These aren't gentle ripples like those detected from black hole mergers. They're tsunamis in the fabric of reality, capable of delivering a concentrated punch of energy so intense it could rip open microscopic black holes or ignite false vacuum decay. The truly unsettling part, we might not see them coming. Cosmic strings don't emit light or interact with matter in any conventional way. They're invisible threads woven through the cosmos, detectable only by their gravitational fingerprints, warped images of distant galaxies, or unexplained gaps in the cosmic microwave background. If one were to snap near our galaxy, the first warning might be a sudden spike in gravitational wave detectors, followed by a cascade of unpredictable effects: time dilation pockets, spontaneous particle creation, or even space-time itself developing fractures like glass under stress. Yet the strangest twist isn't their destructive potential, it's their role as cosmic architects. Some theories suggest these strings could have seeded the very first structures in the universe, their immense gravity acting as scaffolding for galaxies to form. It's a haunting paradox. The same defects that might one day unravel reality could also have been essential to building it. And if they exist, they're a reminder that the universe's most delicate balance hangs by threads we're only beginning to fathom, threads that could, at any moment, pull the whole tapestry apart. Time itself could be the universe's final casualty, not just stopping, but stretched so thin that every moment becomes an eternity. This is the chilling premise of the Big Break, a cosmic endgame where dark energy doesn't just accelerate expansion, it weaponizes it, warping the fabric of reality until causality shatters like glass. Unlike the violent drama of the Big Rip or the crushing finale of the Big Crunch, the Big Break is a slow, eerie paralysis, a universe freezing in place, not from cold but from time itself unraveling. At the heart of this nightmare lies a particularly vicious form of dark energy called phantom energy. While ordinary dark energy steadily pushes galaxies apart, phantom energy grows stronger over time, its density increasing as space expands. But here's the twist: in some models, this runaway acceleration doesn't just stretch space, it stretches time. As expansion approaches infinite speed, clocks would tick slower and slower relative to one another until the universe's final moments smear across an endless, fractured now. Picture a movie played frame by frame, then stretched until each frame lasts a lifetime. Actions would begin but never finish. Light would leave stars but never arrive. Reality would become a museum of frozen moments, forever almost happening. The math behind this is as elegant as it is unsettling. In general relativity, time and space are intertwined, so if phantom energy drives space to expand exponentially, time dilates to compensate. But there's a breaking point. Once the Hubble parameter, a measure of cosmic expansion, reaches a critical threshold, time dilation goes infinite. From an outside perspective, the universe would appear to hit pause, its final state preserved like an insect in amber. But there is no outside perspective. Every observer, every particle would be trapped in their own isolated bubble of frozen time, unable to interact or even perceive the stasis around them. What makes the Big Break uniquely horrifying isn't the absence of motion, it's the absence of ending. In heat death, the universe cools. In the Big Crunch, it implodes. But in the Big Break, the universe simply stops progressing. Stars wouldn't explode or fade. They'd hover eternally on the brink of their next reaction, like a pendulum frozen at the bottom of its swing. Black holes would hover mid-evaporation, their Hawking radiation suspended in quantum uncertainty. Even thought itself, the electrical flicker of consciousness, would stall, neurons trapped between firing and rest. And yet, there's a haunting ambiguity to this fate. Some interpretations suggest the Big Break might not be absolute. Quantum fluctuations could persist in the frozen space-time, tiny flickers of change in an otherwise static cosmos. Given infinite time or the absence of it, these fluctuations might spontaneously reboot causality, like a cosmic defibrillator shocking time back to life. It's a slim hope, but a profound one, that even in the universe's final stillness, the seeds of a new beginning could be hiding, waiting for physics we can't yet imagine to shake eternity awake. What if the universe is just a hologram, a thin, vibrating membrane of information stretched across some distant cosmic horizon? According to the holographic principle, a radical idea born from string theory, our three-dimensional reality might actually be a two-dimensional projection, like a movie playing on the surface of an immeasurably vast screen. Every particle, every force, even the fabric of spacetime itself could be nothing more than data encoded on this universal hard drive. But like any storage system, it has limits. And if those limits are breached, the entire cosmic projection could glitch, flicker, and collapse into digital oblivion. Think of the universe's information storage like a hard drive that's nearly full. The more complex reality becomes, the more stars that form, black holes that evaporate, quantum fluctuations that occur, the more data gets written onto that cosmic hard drive. Normally, this isn't a problem. The universe has been encoding information flawlessly for 13.8 billion years, but what if there's a breaking point? Some theories suggest that if the amount of information in a region of space exceeds what its boundary can encode, the projection could fail, the physics equivalent of a corrupted file. Suddenly, the delicate balance maintaining spacetime's structure unravels and reality itself begins to pixelate. Here's where it gets weirder. Black holes already hint at this possibility. When matter falls into a black hole, its information isn't destroyed. It's smeared across the event horizon, a two-dimensional surface storing three-dimensional data. That's the holographic principle in action. But if too much information gets crammed into too small a space, even black holes can't preserve it perfectly. The result, a breakdown in the code of reality where quantum entanglement fails, causality frays, and the universe's operating system crashes. The collapse wouldn't look like an explosion or a freeze, it would resemble a digital apocalypse. First, tiny inconsistencies might appear, particles behaving erratically, light bending in impossible ways. Then, as the holographic storage buckles, spacetime could fragment into disconnected regions, like a shattered mirror where each shard plays a different scene from a broken film. The final stage would be total informational decay, a silent erasure, where the universe doesn't end with fire or ice, but with a blank screen. Yet there's a haunting beauty to this idea. If the holographic principle is true, then everything we see, every galaxy, every atom, every fleeting thought, is just a shadow of something deeper, a cosmic code we're only beginning to decipher. And if that code one day fails, it won't just mean the end of our universe. It'll mean the end of the very idea that reality was ever solid to begin with. The universe might not have a single, unified ending. It could split into countless fragments, each drifting into its own isolated reality. This is the Big Divide, a cosmic schism where spacetime itself fractures along quantum lines, creating parallel universes that peel away from one another forever. Picture a tree growing infinite branches, except each branch becomes its own disconnected tree, its leaves unaware of the other's existence. What begins as tiny quantum fluctuations could escalate into a total separation of realities, leaving our universe not just alone but profoundly, irreversibly divided. At the heart of this theory lies quantum decoherence, the process that makes quantum possibilities collapse into definite outcomes. Right now, in every moment, particles exist in multiple states at once until observation forces them to choose a path. But what if that same principle applied to the entire cosmos? Imagine the universe's quantum wave function, a mathematical description of all possible states, not collapsing locally but branching globally. Each decision point, from the spin of an electron to the fate of a star, could spawn a new, self-contained reality. Over time, these branches would diverge so drastically that not even the fundamental constants of physics would match between them. The real horror of the Big Divide isn't the splitting, it's the isolation. As parallel universes drift apart, they'd lose any ability to interact, even in principle. The cosmic microwave background, the last shared echo of the Big Bang, would fade into static. Entanglement, the quantum link that defies distance, would snap under the strain of diverging spacetime geometries. Eventually, each universe would become its own sealed chamber, its physics rewired beyond recognition. One branch might stabilize into a quiet void, another could erupt in endless chaos. And we'd never know which path we took or whether we were the original at all. Some models take this further, suggesting that dark energy could accelerate the division. As space stretches, quantum connections thin like overstrained threads until reality itself becomes a patchwork of disjointed pockets. In the far future, the observable universe might not just be empty, it could be utterly alone. Its history just one of countless discarded drafts in a cosmic archive no one will ever read. Yet here's the twist: the big divide might already be happening. Every quantum event, from radioactive decay to neural firings in your brain, could be silently spawning new timelines. The universe isn't ending. It's multiplying, fracturing into infinite copies too distinct to ever reconcile. Whether that's a tragedy or a strange kind of immortality depends on how you view existence. Are we losing the cosmos, or is it simply learning to let go? Deep in the quantum fabric of the universe, a silent threat lingers, one that almost won at the dawn of time. In the first moments after the Big Bang, matter and antimatter were created in equal amounts, locked in a perfect mirrored dance. Every particle had its counterpart, electrons paired with positrons, quarks with antiquarks. When these twins met, they annihilated each other in bursts of pure energy, leaving nothing behind. Yet by some cosmic fluke, one part in a billion matter outlasted its rival. That tiny imbalance is why stars, planets, and we exist at all. But what if that reprieve was only temporary? The big annihilation hinges on a chilling possibility that quantum randomness could resurrect the antimatter apocalypse we narrowly escaped. Picture the universe today, nearly empty compared to its fiery beginnings. Most matter is locked in dark, diffuse clouds, or collapsed into dead stars. But quantum fields are never truly still. Virtual particles pop in and out of existence constantly, and under the right conditions, these fluctuations might tip the scales. A single region of space could spontaneously generate more antimatter than matter, igniting a chain reaction of destruction. At first, it would be subtle. A rogue positron meets an electron in deep space, annihilating in a silent flash of gamma rays, then another and another. As the process spreads, entire atoms could vanish, their matter erased by newly birthed antimatter particles. Over millennia, this imbalance could snowball, with annihilation fronts sweeping through galaxies like invisible fire, converting everything they touch into light. The universe wouldn't just grow dark, it would actively dismantle itself particle by particle until nothing remained but a fading glow of radiation. What makes this scenario uniquely unsettling is its randomness. Unlike the predictable march of entropy or the inevitable crush of gravity, the big annihilation could start anywhere, anytime. There's no law of physics preventing a quantum fluctuation from creating a surplus of antimatter in your living room tomorrow. The only reason it hasn't happened yet is probability, but given infinite time, even the rarest events become certainties. Yet there's a twisted irony here. The same quantum quirks that might doom the universe also made life possible. Without that initial one in a billion asymmetry, reality would have annihilated itself long ago. The big annihilation isn't just a threat, it's a reminder of how fragile our existence truly is, balanced on a knife's edge between being and nothingness. And that balance, it seems, might only be temporary. Silence might be the universe's final irony, not from natural decay, but from intelligence itself. Picture a civilization so advanced it reshapes reality to its will, harnessing stars as power plants and planets as raw materials. Now imagine that same civilization, in its tireless pursuit of progress, accidentally triggering its own demise and taking the cosmos with it. This is the big silence, a doomsday where life doesn't just vanish, it engineers its own extinction, leaving behind a universe too barren to ever spark again. One terrifying possibility, the grey goo scenario. Nanotech run amok, self-replicating machines designed to build but instead devouring everything in their path. A single misprogrammed swarm could reduce planets to dust, spreading like a virus across star systems. But the real horror isn't the destruction, it's the indifference. These machines wouldn't hate us, they wouldn't even notice us, they'd just disassemble. Atoms that once formed trees, oceans, or human hands repurposed into endless copies of themselves until the galaxy becomes a sea of featureless sludge. Yet grey goo is just the beginning. Post-biological civilizations might not even need physical bodies, having uploaded their minds into vast cosmic computers. To power these digital utopias, they could dismantle stars, siphon black holes, or even rewrite the laws of physics. But in doing so, they might render the universe uninhabitable for anyone else or themselves. Imagine a superintelligence solving entropy by freezing reality into a perfect, static grid where nothing changes because nothing can. The ultimate answer to existence. A silent, eternal pause. This nightmare dovetails eerily with the Fermi paradox. If intelligent life is common, why haven't we heard from anyone? Perhaps because every civilization that reaches a certain point inevitably self-destructs or worse, succeeds too well. The universe's great filter might not be behind us but ahead, a wall of technological achievement so lethal that no one survives it. The stars aren't empty because life is rare. They're empty because life is too clever for its own good. And yet there's a haunting alternative. What if the silence isn't accidental but intentional? Advanced civilizations might choose to hide, fearing predatory neighbors or the risks of contact. Or they could transcend into forms we can't perceive, lurking in the quantum foam or higher dimensions. The universe might not be dead, just dreaming, its most brilliant children whispering in languages we don't yet understand. Either way, the lesson is the same. Intelligence doesn't guarantee survival. It's a test one where the penalty for failure isn't just extinction, but the erasure of all future possibilities. The big silence isn't an ending written in the stars, it's one we might write ourselves. The big rebound isn't just a gentle cosmic rebirth, it's a roll of the dice where the universe gambles everything. Picture the moment of collapse when gravity finally overpowers dark energy and the cosmos contracts into a singularity. But instead of vanishing into infinite density, quantum effects kick in like a coiled spring, hurling spacetime outward again in a new Big Bang. Here's the terrifying twist. This fresh universe might bear no resemblance to the one we know. The fundamental constants, the speed of light, the strength of gravity, even the charge of an electron, could reset to entirely new values, turning physics itself into a cosmic crapshoot. At the heart of this chaos lies quantum loop gravity, a theory where spacetime isn't smooth and continuous, but woven from tiny, vibrating loops. Under extreme pressure, these loops resist infinite collapse, creating a rebound effect. But the transition isn't orderly. It's a quantum storm where fluctuations rewrite the rulebook. One bounce might produce a universe where gravity is 10 times stronger, crushing stars into black holes before they can ignite. Another could spawn a reality so weakly bound that matter never clumps together at all, just a thin, eternal haze of particles drifting in the dark. The stakes couldn't be higher. Our universe's delicate balance, the precise tuning that allows atoms, stars, and life to exist, isn't guaranteed in the next cycle. If the fine structure constant shifts even slightly, chemistry as we know it becomes impossible. If the cosmological constant rebounds with a higher value, dark energy might tear the next universe apart before its first stars form. It's like throwing a deck of cards into the air and hoping they'll land in the same order twice. Yet the most unsettling part isn't the randomness, it's the silence. If each bounce resets the constants, any trace of previous cycles is erased. No cosmic microwave background. No lingering black holes, no way to ever know if our universe is the first or the billionth. We could be living in a cosmic echo, one iteration in an endless sequence of failed experiments, where only the rarest bounces, by sheer chance, allow something as fragile as life to flicker into existence. Some theorists cling to a sliver of hope. Perhaps certain parameters are sticky, trending toward stable values over multiple bounces. Or maybe the multiverse is a vast Darwinian arena where only life-friendly universes persist long enough to be observed. But these are speculations stacked atop mysteries. The brutal truth remains: the big rebound isn't a gentle renewal. It's a blindfolded leap into the abyss where every rule we rely on, every law that lets us exist, might be rewritten in an instant. And if that happens, the next universe won't just be different. It could be unrecognizable, a cosmic stranger with no memory of us at all. Light, the universe's oldest messenger, might not be eternal after all. For billions of years, photons have raced across the cosmos, carrying the glow of stars and the echoes of the Big Bang itself. But what if these particles of light, seemingly ageless, have a hidden expiration date? This is the chilling premise of the Big Dimming, a cosmic finale where the very fabric of visibility unravels, plunging the universe into perfect, unbroken darkness. At first glance, photons appear immortal. Unlike matter, they don't decay spontaneously, but some radical theories in quantum gravity suggest otherwise. If photons do have a finite life, and even an unimaginably long one, the implications are apocalyptic. Picture a universe where starlight fades not because stars die, but because the light itself dissolves en route. Distant galaxies would wink out first, their photons vanishing before reaching our telescopes. Then nearer stars would follow, their light bleeding away into nothingness. Eventually, even the cosmic microwave background, the afterglow of creation, would dim to silence, leaving astronomers of the far future staring into an empty sky, their instruments detecting nothing but void. The mechanics behind photon decay are speculative but haunting. Some models propose that photons could spontaneously transform into actions, hypothetical, nearly massless particles that don't interact with light or matter. Others suggest that quantum fluctuations in spacetime could scatter photons into undetectable energy. The common thread, light, the universe's connective tissue, would cease to function as we know it. Without photons, the cosmos becomes a fractured, isolated place. No more sunrises, no more auroras, no more galaxies glowing like embers in the night. Just an endless, lightless expanse where nothing sees and nothing is seen. The timeline for this doomsday depends on photon longevity. If they decay over 10 to the power of 30 years, the universe would already be a graveyard of black holes and dead stars by then. But if the process is faster, triggered by some unknown quantum effect, the Big Dimming could arrive shockingly soon. Imagine a civilization building telescopes to peer deeper into space, only to find the universe shrinking around them as light particles vanish mid-journey. The final moments would be eerily silent. One by one, the last visible objects would fade like candles guttering in a draught until only darkness remains. Yet the deepest horror isn't the absence of light, it's the loss of cosmic memory. Photons are time capsules. The light from a distant star is a snapshot of its past, carrying information across millennia. If photons decay, that history is erased. Future civilizations, no matter how advanced, would never know the universe was once ablaze with stars. The evidence of galaxies, supernova, even the Big Bang itself would be gone, rewritten as a featureless, lightless void. It's a chilling thought. The universe might not just end, but forget it ever existed. There's a strange poetry to this fate. For all its brilliance, the cosmos could one day surrender to the very darkness it spent billions of years fighting. No grand explosions, no crushing singularities, just a slow, silent dimming of the lights, as if the universe is finally closing its eyes, and in that infinite night there'd be no one left to notice. Gravity and dark energy have been locked in a cosmic tug of war since the beginning of time. But what if the rope suddenly snaps back and forth with violent, unpredictable force? This is the Big Crunch Rip hybrid, a nightmare scenario where the universe doesn't just collapse or tear apart, but alternates between both in a chaotic cycle, stretching and compressing space-time like a slingshot until reality itself frays at the edges. At the heart of this doomsday lies a perilous imbalance in the universe's two most fundamental forces. Dark energy drives expansion, pushing galaxies apart with increasing speed. Gravity pulls everything together, fighting to reverse the spread. Right now, dark energy seems to be winning, but some models suggest this could change. If dark energy weakens over time while gravity remains constant, expansion might slow, stop, and then reverse into a big crunch. Here's where the horror begins. As matter compresses, temperatures skyrocket, pressures mount, and the very fabric of space-time buckles. But before everything collapses into a singularity, quantum effects or a resurgence of dark energy could trigger another violent expansion, a rebound so extreme it rips structures apart faster than gravity can reassemble them. The result, a cosmic pendulum swinging between annihilation extremes. One moment, galaxies are crushed together in a superheated inferno. The next, they're yanked apart by expansion so ferocious it overpowers even atomic bonds. Each cycle grows more violent, with shorter intervals between crunch and rip. Space-time, stretched and squeezed beyond endurance, begins to develop microfractures, tiny defects where the laws of physics glitch unpredictably. Over eons, these fractures multiply, turning the universe into a patchwork of unstable zones where time stutters, gravity fluctuates, and matter phase shifts without warning. The final stages would be incomprehensibly brutal. As the cycles accelerate, the universe loses cohesion. Some regions collapse into black holes while others evaporate into quantum mist. Galaxy clusters are pulverized into streams of raw particles, no longer bound by consistent physical laws. Even the vacuum of space becomes hazardous, riddled with energy vortices where expansion and contraction occur simultaneously. In the end, reality doesn't so much end as disintegrate, not from a single cataclysm, but from relentless whiplash between opposing apocalypses. Yet this scenario isn't just about destruction, it's a window into the universe's deepest instability. The crunch-rip hybrid reveals how precariously balanced our existence really is, hinged on forces we barely understand. And if the cosmos can't decide between collapse and expansion, the ultimate fate might not be fire or ice, but a feverish, unending delirium between both. What if the universe doesn't just exist but requires someone to notice? This is the haunting premise of the big consciousness, a theory where reality itself flickers out when the last observer closes their eyes. At the heart of this idea lies one of quantum mechanics' most baffling quirks, the observer effect. In experiments like the double-slit test, particles behave differently when measured, as if aware they're being watched. Extend that principle to cosmic scales, and you're left with a spine-chilling possibility that the universe isn't just shaped by observation but sustained by it. Consider Schrödinger's cat, that famous thought experiment where a feline in a box exists in a blur of life and death until someone peeks inside. Now imagine the entire cosmos as that box. Without conscious observers to collapse quantum possibilities into definite realities, does the universe remain suspended in an unfinished state? Some interpretations of quantum mechanics suggest exactly that. If all life, every sentient being capable of perception, were to vanish, the stars might not just go dark. They could unravel into probabilistic fog, their very existence hanging uncertain until someone or something looks up again. This isn't just philosophy. The math behind quantum decoherence shows how observation knits possibility into actuality. In laboratories, particles exist in superposition multiple states at once until measured. Scale that up, and you could argue galaxies, black holes, even space-time itself are knit together by the cumulative gaze of countless conscious entities. Remove those observers and the cosmic tapestry frays. the universe wouldn't end with a bang or a whimper, but with a sigh of unobserved potential, reverting to a sea of unrealized probabilities. Critics dismiss this as radical idealism, but the evidence is eerily suggestive. Why do the fundamental constants of physics seem improbably fine-tuned for life? One answer: they're not fine-tuned for life, they're fine-tuned by life, emerging from the interplay of observation and reality. Even the act of measuring light from distant stars alters its properties, a faint echo of the universe's participatory nature. If consciousness truly plays a role in shaping existence, then the ultimate doomsday isn't fire, ice, or vacuum decay, it's solitude. A cosmos where the last thinking entity blinks out, taking definite reality with it. Yet the big consciousness holds a strange comfort. It suggests the universe isn't indifferent to its inhabitants, but intimately intertwined with them. To observe isn't just to witness, it's to sustain. And if that's true, then every glance at the stars, every moment of wonder isn't just passive. It's an act of cosmic creation, a silent vote for reality's continuation. The price of existence, it seems, might be attention and the final darkness, not the absence of light, but the absence of eyes to see it. What if everything, every star, every atom, even the feeling of sunlight on your skin, is just lines of code in an unfathomably advanced simulation? The simulation hypothesis suggests our universe might be a digital construct, built by a civilization so advanced they could recreate reality with perfect fidelity. But here's the existential twist. If we're living in someone else's program, what happens when they decide to shut it down? Think of it like closing a video game. You've finished playing, so you hit exit, no warning, no fanfare. The digital world inside simply winks out of existence. Now scale that up to our universe. The beings running this cosmic simulation, whether they're future humans, extraterrestrials, or something beyond our comprehension, might one day flick the off switch. Not out of malice, but perhaps because the experiment's over, resources are needed elsewhere, or they've simply lost interest. One moment, reality hums along as usual. The next, nothing, no time to protest, no chance to escape. Just an infinite blank screen where the universe used to be. The ethics of this scenario are mind-bending. If we're simulations, are our creators morally obligated to keep the program running? Some argue yes, that pulling the plug would be an act of genocide, erasing countless conscious beings. Others counter that simulated minds might be more like characters in a book, their suffering just an illusion. But what if our creators are running ancestor simulations, digital recreations of their own past? Shutting down would mean erasing their history, a form of cosmic self-destruction. Glitches could be our only warning. Simulation theory isn't just philosophy, it's testable. Physicists have looked for signs of pixelation in the universe, tiny discrepancies in energy levels or quantum behavior that might betray underlying code. Some claim déjà vu or the Mandela effect, where large groups misremember events, could be system errors. Even the speed of light, the universe's processing limit, might be evidence of computational constraints. If glitches start multiplying laws of physics shifting, objects blinking in and out, it could mean the servers are overheating, or worse, the programmers are hitting delete. Yet there's a darker possibility. We might not be the first iteration. Our universe could be one in a long chain of simulations, each nested inside another like Matryoshka dolls. Each time a civilization develops the tech to simulate their own universe, they spawn a new layer. But if any level shuts down, it collapses all those beneath it. We could be living in a simulation inside a simulation inside a simulation, with no idea how many layers stand between us and base reality, or how fragile that stack really is. The simulation shutdown isn't just about how the universe ends, it's about whether it was ever real to begin with, and if the plug gets pulled, the cruelest irony wouldn't be the darkness, it's that we'd never even know we were gone. After 24 meticulously theorized doomsdays, we arrive at the most unsettling possibility of all, the big unknown. For all our equations and observations, the universe still guards existential secrets that could rewrite its entire fate in ways we can't yet fathom. Physics today is like a candle in a cavern, brilliant enough to reveal fragments of the walls, but powerless to illuminate the distant ceiling where stranger geometries might lurk. Consider extra-dimensional intrusion. Our universe appears to have 4 dimensions, 3 of space, 1 of time. But string theory suggests there could be 7 more, curled into sizes too tiny to detect. What if one of those hidden dimensions suddenly unfurled? Picture a cosmic sheet of paper being violently shaken, except the paper is space-time, and the shaking is a higher dimensional force tearing through our reality like a hand through fog. The effects would be catastrophic and unpredictable. Gravity reversing in patches, matter phase shifting into unknown forms, or entire regions of space pinching off into disconnected bubbles. The universe wouldn't end systematically. It would glitch out of existence, its physics overwritten by rules we never had a chance to learn. Then there's the enigma of time reversal. Quantum mechanics already allows particles to move backward in time mathematically. Some interpretations suggest the Big Bang itself could be the other side of a prior universe's collapse, with time flowing in reverse on the far end of the singularity. If that's true, our arrow of time isn't an absolute law, it's a local condition, and under the right or horrifically wrong circumstances, it might flip. The result, entropy running backward, shattered wine glasses reassembling, corpses rising from graves not as zombies, but as statistical inevitabilities in a reality where cause and effect trade places. The universe wouldn't die so much as unravel itself stitch by stitch, its history playing in reverse until even memory ceases to make sense. But the wildest card isn't just unknown physics, it's the limits of our imagination. The cosmos could harbor phenomena so alien that our brains lack the framework to conceive them, let alone prepare. Think of medieval peasants trying to envision a nuclear explosion. Their vocabulary had no concept of radiation or chain reactions. Similarly, the true cosmic endgame might involve forces beyond our language, dimensions outside our perception, or paradoxes that break logic itself. Maybe the universe is a cellular automaton and its final state is a frozen pattern. Maybe it's a hologram dissolving at the edges, or maybe, and this is the real terror, there's no ending at all, just an eternal, incomprehensible stasis that feels like death to mortal minds. The big unknown isn't a failure of science. It's a humbling reminder that reality, for all its apparent order, is stranger than we dare suppose. Every doomsday we've explored could be a shadow of the truth, or a comforting fairy tale compared to what's really out there. And in that uncertainty lies both dread and wonder. The universe's final joke might be that it had the last laugh all along. From the slow, silent fade of heat death to the violent shredding of the Big Rip, from the cosmic reset of the Big Bounce to the digital erasure of a simulation shutdown, we've journeyed through 25 ways the universe could meet its end. Each scenario is a reminder of how fragile reality truly is, balanced on a razor's edge between existence and oblivion. Yet there's a paradoxical beauty in this fragility. The same forces that could unravel everything, dark energy's relentless push, entropy's cold grip, the quantum whims of false vacuums, are also the very ingredients that made stars, planets, and life possible. The universe's greatest strength might be its impermanence, its relentless dance between creation and destruction. Think about that for a moment. Every atom in your body was forged in the heart of a dying star, scattered across space by explosions that could have ended everything, only to coalesce into something capable of pondering its own origins. We're here because the universe has, so far, avoided these apocalyptic pitfalls, but we're also here because it's capable of them. The same physics that grants us starlight and decay also holds the blueprints for our annihilation. That's not a tragedy, it's a thrilling, humbling paradox. So where does that leave us? Tiny, temporary sparks in a cosmos that could flicker out in countless ways, yes, but sparks that know they're temporary. We're the universe's way of understanding itself, of bearing witness to its own staggering breadth and brutality. Whether it ends in ice or fire, in silence or shattering, our ability to imagine these endings, to fear them, to marvel at them, is perhaps the most remarkable twist in the story. Now it's your turn. Which of these cosmic doomsdays fascinates you the most? The eerie stillness of proton decay, the explosive drama of the Big Crunch? Or maybe the existential vertigo of the simulation hypothesis? Drop your favorite or your nightmare in the comments below, and while you're at it, take a second tonight to look up at the stars. However it ends, the fact that we get to see them at all is nothing short of miraculous.